I will call it chapter 3, rates of change. So this is really the slow crossover to calculus. When people started looking at how objects are moving, for example, let's suppose we have a function, let's call it s of t, that represents the distance that we travel. So we are traveling some distance. You might have different time values, and then the distance traveled at that time. Let's suppose you're driving somewhere. You start at 0. You haven't traveled at all. Then maybe, let's say time is in minutes or whatever, maybe 30 minutes in, you've traveled, how far did we travel? Maybe not 30. Yeah, sure. Let's say every half hour I take note of the distance that I traveled. There's a lot of traffic maybe. Let's say you traveled 20 kilometers. And then maybe 1 hour in. Let me just backtrack and make this time in hours. So this will be in half an hour. Then 1 hour, maybe you've traveled 50 kilometers. Then 1.5 hours, maybe you've traveled 80 kilometers up to that point. 2 hours, maybe 100 kilometers. Sometimes you go faster and sometimes you go slower. So there is some function that determines how your position, your distance traveled changes as time passes. Now, this table just gives you a little snapshot of that actual function, but maybe you go faster in some points and then you slow down and so on. There's some function behind this. So then you can ask, oh, okay, I want to know how fast I'm going at certain parts. Let's suppose I want to know how fast I'm going over the first hour, for example. So then we can ask questions like average speed. Now I know speed is the change in distance over the change in time. So my average, I need to know, let's say over, I'm just going to zoom out a little bit, I can't see everything. Let's say average speed over time 0 to time 1 hour. Then this average speed is going to be the change from 0 to 1. So the change in distance is 50, and the change in time is 1. So I've traveled 50 kilometers per hour. So I need to know the window that I'm interested in looking at, and then I can find the average speed with a very, very simple calculation that I obtained over that window. For example, if I were to try and see everything, average speed maybe over time 1.5 to time, backwards. From time 1 hour to time 1.5 hours, then that average speed is again the change in the distance. So that'll be 80 minus 50, over the change in the time, which is 1.5 minus 1, giving me, try to squeeze it in so we can see everything, 30 over 0.5, so that'll be 60 kilometers per hour. Squeeze it in. 60 kilometers per hour. Okay, so it's a very simple calculation to find the average speed. Everyone happy with that calculation? Sometimes as we go, one chapter is easier and small, like chapter 3, and maybe another chapter is more difficult. Just because we're going on in the chapters doesn't mean every chapter is more difficult than the previous one. It's as simple as this. Now, graphically, what are we actually doing here? If I have my full distance function, saying how it starts at 0, it's increasing, maybe slowly. I'm not saying this graph matches the table exactly, just a graph. It increases fast maybe, I travel fast, and then I go slower, maybe a lot of traffic, my distance doesn't increase very fast over the time, then it increases faster, and so on. I have this distance function, pretend it matches. What graphically does this average speed represent? Does that have a graphical interpretation? So that I can say this on the graph corresponds to the average speed. Well, it's really given away in that change in distance over change in time. What is this change in distance over change in time? Distance being the vertical axis, time being the horizontal axis. What does that remind you of? So it's an S. Slope. Yes. Nice. So because I have distance and time in my graph, this is exactly the quote-unquote change in y over change in x. So this is exactly the slope of a line. I need to know the window, right? So for example, 0 to 1, let's suppose 1 sits over there, just to make it easy. I am really looking at the slope of the straight line connecting these 2 points. I need to know the window that I'm looking at. So I'll call that the secant line connecting those 2 points. I need to know the 2 points, different other 2 points, other secant line. Once I have the window I'm looking at, the average speed, which is a valid thing I want to know perhaps, is the slope of the secant line. The straight line connecting the 2 points. Okay. So an average is simply the slope, change in y or change in the vertical variable, whatever that may be, but we casually say change in y over change in x, understanding that the variable names could be something else. Everyone happy with the slope of the secant line being the change, the average speed in that function? Change in one, it's the ratio of the change. So now, yes, this comes from having distance over time and looking at speed, but we can now say, okay, well, let's just explain this in general. I don't know where my function comes from. I have some function. It could be a distance function. It could be something else. Don't know. Let's pretend, whoa, that was supposed to be a line. Straight line, like so. Let's pretend I have some function. I just want to look at it. I don't know what it looks like. Whatever, I don't know what it looks like. I have my window, let's say some A to B. I need to know the window I'm looking at. Then I have the secant line between these points. That's what we looked at. And then we're going to call the slope of the secant line is going to be called the average rate of change of my function over the interval a to b. So it depends on where I'm working. If I'm just working with the function, I don't see the function's graph or anything, then we call it the average rate of change of the function, and I need to know the window, of course. If I look at it graphically, then that same concept is the slope of the straight line connecting the 2 points that we call the secant line. And so it depends. Those things are all the same. Am I looking at the graph, talking about its features, or am I just talking about the function's features? Average rate of change. So let's look at a couple of examples on that. It's not a hard calculation, although I am always surprised consistently whenever I put this in a test that many people, I think, expect it to be something more difficult, and they make mistakes all the time when it is the simplest calculation in the whole test. Let's look at problem 3.8, number A, for example. So there I have my function, which is a distance function, 3t squared plus 5. And I'm looking at the interval of t values 2 to 3. So that interval refers to the input variable, which is the t variable in this case. So, I mean, it's nice if you can graph it. It's always nice to look at something, but in no way do we need to be able to graph that for this question. This question is simply asking what is the velocity, average velocity over the given interval. Now there's a little bit more to that question, which we're going to come back to in a second. Right now I'm just doing the average speed or velocity. We're not doing the whole detailed concept, so it's the same for us. Over this interval, that is the change in the, I'll write out, why not? Change in my y variable over change in my quote-unquote x variable. So it's the later function value, so function value at 3 minus function value at 2 over the difference in the time values. And then you plug the 3 into your calculator or do it in your head. I think we do it in our head maybe. Plug in 3, I get 3 squared, that's 9, times 3 is 27, plus 5 is 32. Plug in 2, that t squared is 4, times 3 is 12, plus 5 is 17. I'll leave the 3 minus 2 until we're done. So I get 15 over 1, so 15. Now they don't really tell me the units, so they do actually, meters and seconds. So you could say meters per second, but it doesn't matter. For our purposes, the units aren't super important. We're just practicing the average rate of change concept. Now let me ask you, yes or no, is there anything difficult about this calculation? Anything tricky? No, it's a straightforward calculation. It really should be. And it's a slope, straight lines. We've seen all these things before. I do not understand why in a test people get it wrong. It's the easiest question out of all our questions. Don't always expect the worst. Sometimes the question is just that simple. And in the case of an average rate of change, it's as simple as changing y over changing x. There is no trickery here. Any questions on this? Yes?
I just don't understand how you got the 32 instead of no.
Can anyone verify my calculation? Is the 32 correct?
What was that, an S3 minus S2, or is it 5?
See, this is a 5.
Oh.
This is a 5. This is an S. It's night and day. No, I realized when I call the function S, this is potentially confusion, which is why I made my 5 nice and angled. It's like night and day. My general 5s look like this versus an S, night and day. I don't see the confusion at all. But no, S is not the most ideal name for the function, admittedly, which is why we'll go back to an S. And you can tell me if we should do more, but 3.1, 3.2, the function can change. Let's maybe change the function up a little bit. It doesn't have to be a polynomial. I just did this one because it was our distance function. We could look at problem, I don't know. Let's practice some square roots, why not? Problem 3.3, number 3. Because it has a typo, which is why I want to do that one. My function, I'll call it f to avoid any potential confusion. That 2 should just be at the top. It's an x squared. Not sure how it drifted down. And my interval is 0 to 2. Any other questions? Let me know if I calculate something and it's not right. Verify my calculations for sure. But let's step away from the S5 debate and call a function f or y or whatever. Doesn't matter. So there is a typo potentially in that question, which is why we do an x squared. And if later on you see a 2 as a subscript, it should be at the top and be an x squared. So average, now it's not a distance function, so we then call it in general average rate of change. If it's a distance or position, then we'll call it speed or velocity and those things. But in general, I don't know where this function comes from. I'm just practicing the calculation. So that will be the change in my function over the change in the x values. So then I plug in 2. I get 5, root 5, minus root 1 over 2 minus 0 to show all the detail. You can calculate that. Rounded to 2 decimal places, which is okay for us, especially in the case of a final answer. I can round it with some decimals. 2 should be fine because of the root 5. Of course, I know square root of 5 in my head to many digits, but I'll give you a chance. Who has a number for me? And maybe we need to review rounding, all kinds of things. So it's good to even check the little things. The little things add up.
2.24.
2.24. So, I mean, argue the S5 issues, but actual calculation aside, there really should not be anything tricky here. Nor can I really make it tricky, and I'm not going to. It is as simple as that. So don't expect the worst from every question. All right. Should I put this in the midterm? All right. There is now, this is sort of the first half of it. Now you can go back and say, okay, well that's fine, but if I look at this, for example, and pretend this is the distance function, then I see that over that time window, I might not just want to know what the average is, because sometimes I go faster in that window and then I slow down, and it averages out to something. And an average is always going to sort of smooth out the detail. There's a danger in an average calculation. An average is always going to hide the detail. For example, if I focus on the traveling issue and the distance changing, so over time, S of t, let's suppose I have my time window here, and let's suppose my speed is very consistent. Actually, very slow. Let me back it up, maybe make it a little more interesting. Like I actually make progress somewhere. But I do it in a very gradual, consistent way. It's not, of course, perfectly straight. And if I draw the secant line between those two, you see, yeah, okay, sometimes I do go a little faster in the beginning and then I slow down, and the average is very close. Average speed is close to the actual speeds that I had during that time interval. Not exactly the same, because it is an average and it's taking all the different speed values as I'm driving and smoothing them out, merging them in some way. So I get some sort of average. But I could have driven a very different way and the average could be the same. If I have my 2 points here, exactly the same, I could have sped up and then slowed down and then sped up again. The average is going to be exactly the same. So it's the same average speed. But the same thing did not happen. Very different things happen. The average doesn't convey the information of the detail inside that time interval. It just merges it all together. And I might want to know, how fast was I going right there? Did I erase this? No, now I erased it. There you go. Right there, how fast? Or right there, how fast? The average is not a sufficient way of being able to pinpoint a speed at any given time. It is a simple calculation, but it has that drawback of smoothing out the information, and I don't know the detail, and maybe I want to know the detail. What do I do? Well, I'll make a new page first, so that I have space to draw a new graph, and let's keep the graph nice and simple, with not anything too wild up and down. So let me just go back for a second here. I may want the speed at a specific time, specific point in time. We'll call that the instantaneous speed. And in general, we'll call it the instantaneous rate of change. If it's not a matter of speed and just having a function that changes, I'll call it the rate of change. And if I'm interested in just what is happening at the specific point, then we'll call it instantaneous instead of average. Okay, so just a point. The problem is the average calculation, which is simple enough, looks for a change between 2 points. And then does this calculation up here. I need to have 2 points to do any sort of calculation like this. And that's all I know how to do. So let's use that and see what we can do. I want to make this graph nice and big. Let's go back to x and y. Let's suppose my function is That's a little too flat. I'm going to redo that. But curvy, yeah, it's a little better. So here's my function. And let's suppose I want to know at this A exactly what is the rate of change right there. So I want to know or find the instantaneous rate of change of my function at x equals a. That's the question. And I don't know how to do that. But it turns out to be a very important question that needs figuring out. Is everyone happy with the question? And how the average doesn't answer that question? We need to understand what the issues are and why we are here to make sense of how we'll proceed. This question is not the same as the average rate of change. Does everyone agree with that? Because the average has a window, and I have now the issue of finding a specific point. So I can only use what I already know. And what I know is what to do if I had 2 points. So let's suppose I have another point. I know I'm changing the question. Let's suppose I have another point. Then I know what to do. I connect the two and look at the secant line. So I'm just going back and using what I already know. So instead of we are trying to answer the actual question, but instead of doing it, I don't know how. So instead, I'm going to look at, I'll call it a window, or it's an interval of x values, A to B. And find the average rate of change instead. Because I can do that. I know how to do that. I'm just going to make one little adjustment, which is going to make things better in the long run. And instead of specifying another point, I'm going to specify how far I step forward and call that h. Either way, I have another point here, and in this case, it's going to be a plus h. So I'm just going to update this as well. It's just another way of getting a second point. Instead of picking the point, I'll pick the step forward, and that also gives me the second point. Any questions on the h and what that means? I just don't want to actually say what the point is. I'd rather focus on the step forward. For reasons that'll make things easier later. A little later. All right. I can do this average rate of change. It's going to be the change in the y value, which is the later function value minus the earlier function value over what? Over h. So the convenience of doing it this way is that my denominator is going to be h, because that's the change in the x direction. And it's just going to make that calculation look a little simpler. So I can focus on the top, and the h at the bottom is very straightforward. But then you say, okay, well, great, but this doesn't answer my question in any way. I'm looking at what happens just here. And this average, which is the slope of the secant line, which I can calculate, has all this information as well. And I don't care about that. I care about what happens only at h. So this extra information of how I travel is changing the average speed number that I'm going to get. All right, fine. I'll say, okay, well, let's not step that far ahead then, because it's using too much information I don't want. Let's not do that. Let's step forward just, oops, back to the pen. Let's step forward a little less, maybe over there. Let's call this H1 because I'm going to have multiple H's here. And let's step forward a little bit smaller distance. Then here I'm going to be left with a second point that's A plus H2. It's going to give me a second point that's closer to, sorry, that line could be better. That's a point that's closer to my point of interest, even though I'm still using information in the average, information I don't want, it's less than before. So it is an improvement, definitely. So this is sort of the first thing. Then I'm going to look at a smaller window by not stepping ahead that much. And then the average rate of change is the change in the y value. So the later function value minus the earlier function value over the h value in question. Is everyone happy that I am making an improvement and I'm trying to estimate what is actually happening only at A? But I have to sort of have a trade-off because I can only do an average calculation. I need to have a window which then uses more information in that average calculation, which skews my view of what's actually happening at A. But by limiting that information, I am making a better guess at what's happening at A. Does that make any kind of sense? That the second one is a better guess than the first one. Okay. But it's still not great, especially if my graph goes up and down a lot. This is a nice smooth graph. So then you can say, okay, we're going to do it again. Whoops, erasing time. Why don't we do it again? And keep stepping closer and closer and using less and less information in my approximation. Let's say I want to step only a little bit. Now I can't make it too little because then I can't see what's happening anymore, but we can just keep doing that. And you see that this straight line that I'm drawing now is much closer to the actual graph. The information that I'm using is much less and much more accurate. So I'll write it one more time. Zoom out. So we can look at an even smaller window by decreasing the forward step h. And again, it's an average calculation, which I need. It's the only thing I can do. I have a window. Average rate of change is then change in the y value, which is the later function value, and we start to see the pattern here. The h is the only thing that's changing, right? Okay. Good to have a big picture of what is happening here. What am I doing? Now I can keep going, but I'm running out of space to actually see my drawing, and the zooming in is not going to help. You can imagine I keep going, making that window size smaller and smaller and smaller. I'm using less and less information, closer and closer to just what's happening close to A, and my approximation is going to get better and better. These are all approximations. The trade-off, simple calculation, but it's an approximation. And I can keep going like this. Dot, dot, dot. Keep going. I can keep going forever. Forever. making, or by making h smaller and smaller in size. If I said h is getting smaller and smaller, that means h is approaching 0. H will never be 0. Because if h is equal to 0, then I don't have a window, I have only one point, and I need a window to calculate an average. So I'll never actually get there. But if I look at these approximations, let me zoom in. This was the first approximation. Then I made the window smaller. Better approximation, better approximation. The smaller I make h, the better and better the approximations get. Let's write that down. So as h gets smaller, if the function behaves nicely, the approximations, I'll squeeze it in here, all the average rates of change calculations looked like that, gets closer to the instantaneous rate of change at x equal to a. I can't get there. I cannot calculate it. It is impossible. Because in my calculation, dividing by 0 is not allowed. But I can look if there is a pattern, if there is a trend, as h gets smaller and smaller. How does this approximation behave? Keyword behave. And when I look at the behavior of something as something else changes, what is our mathematical word for that? This is awkward. Starts with an L. Has 5 letters. Limit. It is the limit. So, here's the punchline. The instantaneous, I have to sound this out every single time. Instantaneous rate of change of my function at a single point A is the limit as h approaches 0 of this average rate of change. Not that I care at all, but in case you see it in the book, this is called the difference quotient. I honestly don't care, but I have to care because that's what it's called. I'll never use it. In case you see it somewhere, they're only talking about that average approximation. So, well, look at that. Limit. And there was a point to doing limits. The limit. Because I am looking at the behavior of that slope of the secant line as the window gets smaller. If that behavior points to a specific number, that is the instantaneous rate of change. That is what's happening exactly at that point. But I can't ever calculate what's happening at that point. I can only look at the behavior. Thoughts and questions? Maybe you're not sure until we see this actually in an example. Let's start with a graph that we can actually look at, something simple. And a polynomial is definitely a good first one to look at. So let's look at problem. I'm just looking for an easy function. Let's go here. Oh, look at 3.9. There has to be something nice in 3.9. Yeah, number 2 is pretty good. Number 2 is pretty easy. there my function is, I'll just write 3x plus 1 because I like the x term first. And my interval is 2 to 4. So they have two questions here. First they ask, what is the average rate of change over that interval? And then what is the instantaneous rate of change at, find the average rate of change as well as the instantaneous rate of change at the left endpoint. So just at x equals 2. Let's just picture, okay, no, I don't like this one that much. Back it up. Back it up. Number one's better. Straight line might not visually look very nice. I want something with a bend to it. You should always write in pencil anyway. You should never commit what I say in pen. That's a risky game. Let's change my mind. Okay, so let's maybe see it over here. This graph, I can focus on the first quadrant because it's 1 to 2. This is just a couple of transformations. Stretch it vertically, shift it down by 1. No problem. That's maybe too wide, isn't it? What is the y value when x is 1? Yeah, they're all positive, isn't it? Too wide. My parabola isn't that wide. Let's make it. I'm just going to put it like this, maybe. And let's just say 1 is over here and 2 is over there. Might not really be to scale, but regardless, it's okay. I'm not going to draw the secant line because this guy is sort of straight, close to straight already. But average rate of change over the given interval, very simple. F the second function value minus the first, second x value minus the first. Super easy. You can just give me the final answer. Depending on the complexity of the function, sure, be careful to get the correct function values, but still it's not a complicated setup in any way. Final answer. This should not take that long. Someone say a number. 6? Okay. But now pretend this is more bendy. If I want to know exactly what is happening at 1, I'm using a whole big window of information that skews what's happening at 1. This is not a good approximation. I now know that the instantaneous rate of change at x equal to 1 can be obtained by looking at the limit h goes to 0 f of 1 plus h minus f of 1, because the 1 is my point, over h. That setup, that limit, you have to memorize. You have to just memorize. Limit h goes to 0, f of a plus h minus f of a over h. Write it 10 times, do whatever you need to do, but you just memorize it. I don't want to relive this whole thing every time to get to the end. If you want to understand where this comes from, sure, here it is. But we do it once and then we move on, using this limit definition for the instantaneous rate of change. So we have to memorize it. No way around it. Okay, well, there is an extremely long way around it, sure, but nothing that I want to do. Okay, so the first thing I want to do here is simplify by using what the function is. So my function is, zoom out, yeah, I can see them both, yeah. My function is 2x squared plus 1. If my input now is 1 plus h, that goes wherever x goes. Let me zoom out a little so I can see them both. And it's going to be 2 times 1 plus h squared minus 1. I'll put that in square brackets. That's my first function value. Minus f of 1, which I know we've already found is going to be a 1. All of this over h. Now I will simplify. I'll do not too much in one go. The 1 plus h, everything squared, is the first one squared. Product of the 2 times 2, second one squared. This minus 1 and that minus 1 is minus 2. All over h. Let's get it in the last couple of minutes we have left. This is something that is going to take a while, even for this simple polynomial. Now I multiply the 2 in, I get 2 plus 4h plus 2h squared minus that last 2 all over h. You have to, while I'm simplifying the numerator, you have to write limit every time. You have to put it all over h. Those things are just waiting for me to be done with the simplification. And of course you can show as many or as few steps as you want on the way. This is just enough detail, I think, for our first example. But it depends on the function, it depends what I have. I have to write limit every time, because the behavior of each of these expressions, each of these functions are the same. The 2's cancel, and I have 4h plus 2h squared over h. There is my function. This limit doesn't care what the original function is. This is a function in h because the limit is asking for h changing. So for the moment, there's no x, there's no original function. I'm trying to find if this limit has an answer. Does it exist? What is the form of this limit? I know we're running out of time. What is the form of this limit? Well, I plug in the 0 value for h, I get 0 over 0, which means anything can happen, which means I need to simplify. And luckily, the simplification is pretty straightforward. I can factor out an h at the top, 4 plus 2h left over an h, and the h's cancel. Then I have only 4 plus 2h, and that's a polynomial in h, which means I can plug it in. It has no problem. It's a 4. It exists. Yay! And, zoom out more. If I compare that, I see the original 6 approximation by way of the average rate of change wasn't even close to what it actually is. It's actually a 4. So yes, these are tedious. No, there's no way around it. You just have to practice. Memorize the limit setup, and then I just have to go through the motions and see. You'll see similarities. It's always going to be form 0 over 0. Always have to simplify in some way.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.